How are you guys doing today? I'm Rocco Aquilino. This is Raymond Koba.
Howdy.
And we're going to teach you a PowerPoint on lenses. And the thing is, we're going to teach it to you guys better than Mr. Schoening did.
There are two types of lenses. There are convex lenses and there are concave lenses. Convex lenses are shaped like an oval and are thicker in the middle. They can also be called converging lenses. Concave lenses are thinner in the middle and are shaped more like an hourglass. The rays refract through the lens and converge toward the focal point for convex lenses. For concave lenses, the rays refract and diverge. These diverging rays then are traced back towards the focal point to create a virtual image. Now I'll be going into more detail on converging lenses. Like I said before, converging lenses or convex lenses are shaped like an oval. These types of lenses can create either real images or virtual images. Every real image created by a convex lens must be inverted. Also, every imaginary image created by convex lenses must be upright. Whether the image is real or imaginary depends on the object's distance from the focal point.
Now I will be showing you how the focal point is important and why the object's distance away from the focal point is significant. On these diagrams, the 2f stands for 2 times the focal length, as the f just stands for the focal length and the focal point. The object in this diagram is placed behind 2 times the focal length. Therefore, when it goes through the lens, the image is smaller, inverted, and real. In this diagram, the object is placed on 2 times the focal length. Therefore, when the light rays go through the lens, the image is the same size. However, it is still inverted and real. In this diagram, the object is placed in between the 2 focal points. When it goes through the lens, the image is now bigger than it was before, but it is still inverted and real. In this diagram, the object is placed directly on the focal point. There is no image formed. We will show you later in the simulation why there is no image formed. In this final diagram, the object is placed before the focal point. Therefore, the light rays are not going to connect and create an image past the lens, and it will create an imaginary image that is bigger and upright. In this slide, I'm going to show you 8 different scenarios where an object is going to be placed and an image is going to be formed. The red lines indicate where the object is placed, and the blue lines with the same number is going to show the image that is formed. For the first and second objects, they are placed behind twice the focal length. When they show up as the image through the converging lens, they are both smaller than the original object. However, they are still real and inverted. On the third scenario, the object is placed directly on twice the focal length. Therefore, when the light rays shine through the object and go through the lens, the image is the exact same size as the object is. It is also real and inverted still. Now, for the fourth and fifth objects, they are both placed within the focal length and twice the focal length. When they are shown through the lens, they are both magnified, which means bigger, just in case you didn't know, because I know Schoening doesn't know that. However, they are still, like I said for the past 20 times, inverted and real, so this should be sewed into your brain. For the sixth object, it is placed directly on the focal point. Like I said before, we will show you in the simulation why no image is formed. It gets kind of funky. However, this is kind of where the breaking point of real and imaginary happens. Kind of like the Bed Bath & Beyond section, like Beyond, you know? Now for the seventh and eighth objects, these objects are both placed in between the lens and the focal point. Now as you will notice, there are no images over here for 7 and 8 as they are placed over here. When they are placed before the lens, that means they are imaginary. And when they are imaginary, for a converging lens, they are always going to be bigger and upright. They're not going to be inverted like past the focal point.
Now, moving on to diverging lenses. Diverging lenses, or concave lenses, are thinner in the middle and are shaped like an hourglass. The images that are created by diverging lenses are more uniform. This means that the images are always imaginary, they're always upright, and they're always smaller. See, that's a lot easier than the varying converging lenses as before.
Now I'm going to explain the diagram for diverging lenses. This one is a lot less complex than the converging lenses. We're only going to show you 5 scenarios because each scenario is about the same. The first 2 objects are placed before twice the focal length. And as you can see, the blue lines here, 1 and 2, are both smaller, upright, and imaginary. The focal lengths, or the focal points, really aren't relevant when it comes to determining the image. Now on to the third and fourth scenario. These 2 are both placed in between the focal point and twice the focal length. Now just like the first and second images, they are smaller, upright, and imaginary. And this includes the 5th one as well. It is placed inside the focal length and the lens, and it is still smaller, upright, and imaginary. Now, when it comes to seeing these, a diverging lens, you're always going to know that when an object is placed, it's always going to be smaller, it's always going to be upright, and it's always going to be imaginary.
In order to solve problems for lenses, you need formulas. There's only 2 main formulas that you use while solving problems for lenses. There's a magnification formula and there's a focal length formula. The magnification formula can determine many things. You can determine the height of the image, the height of the object, the distance of the image, and the distance of the object. M represents the magnification. The magnification equals the height of the image over the height of the object. It also equals the distance of the image over the distance of the object. You must be wary, though, of the sign of your final answer, because one of the formulas must be negative. That is what the plus or minus means. The next formula is the focal length formula. With this formula, you will be able to determine the focal length and also the distance of the image and the distance of the object. This formula gets a little tricky because you work with inverses, but it is also helpful to find these variables.